Okay, we are now going to start our lecture number 22. We have, after this one, we're going to have 2 additional lectures to go to conclude our course on advanced electromagnetics. And today, we are going to look into Poynting's theorem for harmonic fields. How it's going to look like. You are going to use that theorem to understand how energy is exchanged between different parts in a volume, And we are going to talk about Helmholtz equation, which is the counterpart of the wave equation for the case of harmonic fields. Then we are going to derive a solution of this equation, which is going to be the plane wave in vacuum, plane wave for an harmonic field in vacuum. And then we are going to talk about power, density, energy, and we are going to look into the relations between those quantities. The references for today's class is Jackson's sections 6.9 and 7.1, Jackson's classical electrodynamics book, and our ebook part 2, chapter 7. Always reminding you, this ebook is available, right, at our webpage lsi.ufpe.br. / Fontana. Then we have the 2 ebooks, Electromagnetismo, part 1, and Electromagnetismo part 2. Okay, and these ebooks are written in Portuguese language, right? But if you speak a different language, you can open, these are all in HTML. You can open the ebooks using the web browser, Chrome, and with the Chrome you can translate the web page that you open. So you can translate to your own language, English, French, or whatever it is, okay? So that's a good, helpful tool for you to read other things, things that are written in different languages. The equations are not translated, they are the same. So you can pretty much understand what is written in there. Okay, let's start with our lecture. We are going to look into, when we talk about energy and power, right? Power and energy, we always have a dot product or a cross product between vector quantities, between field quantities, which are vectors. Of course, we can have a product between scalar quantities. And if we assume harmonic fields, we are interested in average values, right? We know already the time dependence of quantities, either scalar or vector quantities. Then we want to have a time varying quantities. For instance, if you look, for instance, at a quantity that is, let's say, a scalar quantity, f, we can, if we assume the time dependence with the frequency omega, let's say, so we can always write a scalar quantity as the real part of a complex number f exponential of j omega t, right? If f is real, just reminding what we did before, then we have f equals to f cosine omega t. So if we have if f has a pi over 2 phase, let's make minus j pi over 2, then f is going to be f sine of omega t. So I have an harmonic, time dependence with either with cosine or sine or a combination of those two. And in fact, we want to know in a cycle, okay, since when you have a full change in a full period of the time function, what's the average value? Of course, the average value is 0, right? But sometimes we have products of two quantities, f times g, okay? And this is equals to the real part of f, right? Times the real part of g. Or if you want, you can write f as 1/2 of, I'm sorry, this is different f here. The round f and the, fg. We have 1/2 of f exponential plus the conjugate, and g the same thing, right? Then the product fg is going to be 1/4, right, of fg exponential of j to omega t plus the conjugate. Then you have a cross product here, f and the conjugate of g, but then the conjugate of g exponential is going to be g times exponential of minus j. So you're going to have also terms like this, 1/4 of fg conjugate, no time dependence plus the complex conjugate, right? So that's what fg is. It changes with time, with twice the frequency, right? But we want to know, in general, what is the average value of, product quantity. So what is the average value of fg over a period? So by definition, that would be 1 over the period, integral over 1 period of dt fg, right? So that's going to be 1 over t, integral from 0 to t. T is 1 period, so recall that t equals 2 pi over omega. So it's going to be dt. Then we have all those terms that I just showed you. You have fg exponential of j twice omega plus conjugate, right? You have a factor of 4, right? 1/4 plus 1 over t integral of dt over 4 fg conjugate plus the conjugate of that, right? Well, the integral of the exponential of j to omega t over a period is always 0, because the average value of cosine of 2 omega t or sine 2 omega t is equals to 0, right? So this is going to be 0. And here we have, the integral of dt equals to the period. This is a constant function, so this is going to be 1/4 of fg conjugate plus complex conjugate, right? So that's what we have. So that's 2 times the real part, right? So that's going to be 1/2 real part of fg conjugate, or the real part of 1/2 of fg conjugate. So this quantity fg conjugate over 2 has a meaning, okay? So we can consider that quantity, let's say h, this complex number, 1/2 of fg conjugate. This h has a meaning. What is the meaning? Well, the average value of fg equals to the real part of h. That's the rule. So if you want to consider the field, time quantities f and g, you want to know the average value of a product, then you do fg conjugate divided by 2, define that quantity. So the real part of that quantity is going to give you the average value. Okay? So what happens here, when you have Poynting vector, we have a Poynting vector let me see just quickly here. What is this? Oh, okay. We have one quantity, one important quantity is the Poynting vector. Okay. Let's just see here quickly. What is the scope of this thing here? Yeah. Okay. Well, we spoke before about the Poynting vector. Let's look at it. Poynting vector. Poynting becoming complicated here to handle this thing here. Let me see what can I do. Yeah, okay. The Poynting vector for a time varying field, right, equals to E cross H. And what we do, I mean, for time varying fields, arbitrary variation. So let's do the same thing. So E equals half of E exponential plus the conjugate, and H equals half of H exponential of j omega t plus conjugate, right? So we can make the cross product. We are going to have the same things that we just did for the scalar quantity. So we're going to have E cross H equals to a quarter, right, of E cross H conjugate plus the complex conjugate, doesn't depend on time, plus 1/4 of E cross H exponential of j2 omega t plus conjugate, which depends on time. So if we make an average value of the Poynting vector over a period, we have the same result. I mean, the average value of the Poynting vector is going to be 1/4, right? So we're going to have E cross H plus the conjugate, because the average value of E cross H equals to E cross H, because it doesn't depend on time, plus the conjugate, right? And the other things are 0, right? Because the time average is 0. So this is going to be 1/2 of 2 times the real part, because this equals to the real part of E cross H conjugate. So this equals to the real part of 1/2 of E cross H conjugate. Okay, so average of the Poynting vector is the real part of this quantity here, which we are going to call the complex Poynting vector. By definition, is 1/2 of E cross H conjugate. Watts per square meters in the SI unit system, right? So this is a complex vector, and the real part gives the average of the Poynting vector in time domain. Right? So that gives the real part equals to the active power density, the average, right? Average active power density. Okay. So let's derive the complex Poynting's theorem, right? So what we are going to do, the quantity of interest is this quantity here, okay? So what we want to do is to calculate the divergence of the complex Poynting vector and expand that. So that's going to be 1/2 of the divergence of E cross H conjugate. Okay, so we have an expansion for this. Okay, I always use that expansion. Let me demonstrate to you what that really is, just to give you a clue how to do those demonstrations. I mean, how to derive, how to check what is the correct expression for this expansion here. So let's consider separately here how to calculate divergence of A cross B in general, okay? What is this expansion here? So it's very easy to calculate this using the Levi-Civita symbol, because when you do cross products, we always use, I mean, you have to guarantee that for instance, A cross B, right? Using Einstein's convention, in which repeated indices indicate a sum, right? So that's going to be AI Bj epsilon I j k ak. So that's what it is. So this means, this thing here means sum in I equals 1 to 3, sum from j equals 1 to 3, sum from k equals 1 to 3 of AI Bj, Levi-Civita symbol, epsilon I j k ak. So you see that our indices here are repeated. I appears twice, j appears twice, and k appears twice. So it's a triple sum. So the Levi-Civita symbol I'm just not sure if it's double T or if it's single T. Let me check here. Levi-Civita, yeah, single T, not double T. Sorry about that. Levi-Civita symbol, epsilon j k l, right, equals to plus 1 if j k l is a cyclical sequence from starting, right? Starting at 1 to 3. So any cyclical permutation, 1 to 3, 2, 3, 1, 3, 1, 2, and so forth, is a cyclical, gives a 1 result, equals to 0 if any for repeated indices, and equals to minus 1 if JKL is not a cyclical sequence. Okay, 1, 2, 3, if I make 2, 1, 3 is minus. So that's very useful for vector products, right? I mean, I can always write in a very compact form the cross product between A and B like that. So what would be, let's make it in rectangular coordinates. W divergence of A cross B equals to the dot product, right? AI nabla I, the ith component of nabla, dot, well, the I, let's make an L component. So that's going to be epsilon j k L aj bk al. But L has to be equals to I in rectangular coordinates. Notice that if I don't use rectangular coordinates, I have to make derivatives of the versors as well. So I'm going to use the rectangular coordinates so I don't do that complication. If I demonstrate this chain rule in Cartesian coordinates, that's going to be valid in any system, any reference, any coordinate system. So let's do, so here I have to use L equals to I, right? So this is going to be nabla I epsilon j k I, right? aj bk. So that's what it is. The epsilon can be put outside of the operation, jki. So I have a chain rule here, nabla I aj bk. Okay? So it's going to be epsilon jki. Then I have a chain rule for the derivative of a product. This is going to give me, in fact, bk, derivative of aj plus aj derivative of bk. So that's what we have. So let's copy this thing here and move to the next page. Okay. Go to the next page. That's what we have so far. So forth. Now I'm going to play around with the properties of, we see that here we have a sort of dot product here, okay? Oops. I think I made typo here. What is this? Oh, sorry. This is JKI, right? I can play around with the indices. For instance, if I make permutation in the indices of the Levi-Civita symbol, if I make cyclical permutation, I have no modification in the symbol. It's the same. Notice this is a triple sum here, okay? All indices. So I can play around with the indices are dummy indices. I can always play around, but I cannot violate the cyclical property. If I change in a non-cyclical way, I have to change the sign, okay? So, here we are going to have a dot product of bk with the kth component of a curl. Let's see how it is. This is going to be bk epsilon jki nabla I aj plus epsilon, I'm just repeating here, jki aj nabla I bk, right? So here, I have ij, I'm going to make this equals to epsilon ijk, right? The same thing. So you see that epsilon ijk nabla I aj equals to the curl of A at the kth position, right? ijk, epsilon ijk is the kth element. So this is going to be exactly B dot curl of A. So we have to make the sum, right? Recall that I'm doing a sum. Here, on the other hand, I have aj epsilon jki nabla I bk. So I'm going to change j and I here. So that's epsilon I jk, right? So there's the same thing. I made a cyclical permutation. Now I'm going to make a cyclical permutation here. So it's going to be minus epsilon I k j, right? So jki and ijk have the same sign. Now I made a cyclical permutation, change the sign. Epsilon I k j, so nabla I bk. Well, you see that this is I k j is the cross product of nabla with b in the jth elements. Okay, so we have here aj times that, which is a dot curl of b. So that's the identity, right? The divergence of a cross b equals to b dot curl of a minus a dot curl of b. You see, that's how it is. The chain rule, if this was a mixed product, let's say a dot b cross c, we could make cyclical permutation for the mixed product without changing it, right? That would be c dot ab, which equals to b ca. It's the same. But here we cannot do that because we have a derivative of a product. A derivative has, you have to make a chain rule. So that's why we have two terms, and not only one like the traditional mixed product. And also, you see that to remember this identity, you see, if we make a cyclical permutation, b dot, then you make a b dot, right? B goes there. Then the dot, right? Change with the cross. B dot curl of a. So it's a cyclical, it's a positive permutation. Then you change the position of a, b, you have minus. That's the rule, okay? So all of this, just to remember, we always use this identity. We never demonstrate it, but that is easy to demonstrate it. There's some more complex ones that are more difficult, but those are simpler. So going back to our lecture notes, let's look at Poynt's theorem. So what we have is we have S, right, equals to 1/2. That's a complex Poynting vector, E cross H conjugate. So what we want to calculate is the divergence minus the divergence. We want to calculate the flux inwards a closed volume. So minus divergence of S equals to minus 1/2 divergence of E cross H conjugate, right, equals to minus 1/2 of, then we are going to use H dot, right, H dot, H conjugate dot, curl of E, minus Z dot, curl of H conjugate. Recall the equations, right? Curl of E equals to, in the harmonic domains, minus j omega b, okay? And curl of H equals to j plus j omega d. Then if I make the conjugate, it's going to be j conjugate minus j omega d conjugate. So let's do that. This is going to give us minus 1/2 H conjugate dot curl of E, which is minus j omega b, minus E dot curl of H conjugates right there. So we have a J conjugates minus J omega D conjugates. So then we have equals to, that's going to be a plus, right? J omega, let me see, I have a 1/2, right? Over 2 is this right? Yes, 1/2, 1/2, yes. So over 2, so you're going to have BH conjugate, right? Then we have plus EJ conjugate over 2. Then we have a plus and a minus. Minus half of J omega ED conjugates. Okay? So I can write this like this, equals to half of EJ conjugates. These are all complex quantities now. And I'm going to put the 2J omega, not plus, but like this, minus J2 omega. Okay, so I'm going to have ED conjugate divided by 4, right? Because it's divided by 2, right? Minus, then minus BH conjugates divided by 4, right? So now integrate, so we have minus S minus divergence of S. So we integrate in the volume and apply Gauss's law. So this is going to be the flux inwards from of S. Okay, so we're going to have a closed volume. We have a fields for propagating space. We just calculate on a closed volume, V. The element outwards is the area, differential area is the sigma, right? So we have this, this volume here, right? So that's an area sigma here, right? So so we calculate the flux of S inwards. So the integral from the divergence is going to give us the minus the flux of the complex Poynting vector equals to 1/2 EJ conjugate, right? There's one term minus J2 omega. Then you have something that we call the WE capital minus WM, which are complex numbers. These are called complex energies. WE capital, capital W, equals to the integral in the volume of lowercase w, and Wm is the integral of the complex energy density, Wm. And these complex energies, you see, this is the Poynting theorem here, in complex form. So we have some interaction with carriers, then some storage, energy stored or loss, depends on the, that's going to depend on the type of media you're going to look into that. So the energy density now is a complex number, which is 1/4, right, of ED conjugate. Why is that 1/4? Well, because the average value, right, of the energy equals to the real part of You recall that just remember here, energy density in time domain is 1/2, right, of E dot D. So average value is half of half. That's why we have a quarter. When you have the real part of this, is going to be the stored energy average value. So average value of WE equals to the real part of WE. That's what it's going to be. Because we have 1/2 of the definition plus 1/2 that comes from the average value. So that's going to be exactly the real part of that, right? If I didn't have 1/2 here, I would have 1/2 there. So that's what we have. And also, Wm is the real part of the energy density, Wm, and these are the energy densities, complex quantities in general. Okay, so that's what we have. We have, so in differential form, let's say, Poynting's theorem the differential form of Poynting's theorem for harmonic field is minus, I can put the minus if I want, divergence of S equals half of EJ conjugates minus J2 omega density, energy density, electrical energy density minus magnetic energy density, right? And the integral form equals flux inwards as sigma equals to the energy exchange between field and free carriers, which is this integral here, and the integral of the other term goes to W capital, right, minus Wm. That's the net energy, let's say, electric minus magnetic. If those are equal, we don't have an imaginary part of the complex flux of power, right? So that's what we have for harmonic field. That's how the Poynting theorem is, both differential form and integral form. Okay. We're going to explore that when calculating the loss in the magnetic media in the next lecture. Okay. Let's look now into Helmholtz equation. And let's look what is the solution. Let's go to this next topic. Let's assume that we are in vacuum. Okay. We have no sources, no charge density rho equals 0, no current density J equals 0. So we have B equals to the magnetic permeability in vacuum times H. D equals to epsilon 0 E. So what we have in that case, we have a curl of E equals to minus J omega mu 0 times H, right? Divergent of E equals 0, right? That's the second equation. Curl of H, there's no current density, equals to J omega epsilon 0 E, and divergence of H equals 0, right? So we can now apply the curl in either this equation or in that one. So we're going to have that double curl, let's say on E, Okay, it's going to be gradients of divergence of E minus Laplacian of E, right? So when I have the curl of the curl, it's going to be the curl of H, which is right there. So this is going to be minus j omega mu 0 curl of H, which is j omega epsilon 0 E, which equals to j squared is minus 1 times minus this plus omega square mu 0 epsilon 0 E. Divergence of E, on the other hand, is 0, right? So we have minus Laplacian. This is equals to 1 over c squared. This is omega square over c square E. Okay? And this number, so we're going to have Laplacian of E plus, right? This goes to the right-hand side as plus omega square over c square E equals to 0. And this quantity has dimension L to the minus 1, length to the minus 1. We call it the wave number in vacuum. By definition, is omega divided by c. This is defined as the wave number. In fact, it's all together, wave number. We're going to interpret these quantities in a while. C, as always, right, again, I think we did that before, but let's do it again. C equals to 1 over root square of mu 0 epsilon 0. Mu 0 is 4 pi times 10 to the minus 7 Henry per meters. Epsilon 0 equals to 1 over 36 pi approximately, right? Times 10 to the minus 9 farad per meters. So the product is 1/9, right? Times 10 to the minus 16 Henry farad per square meters, which is going to be the corresponding unit, right? And the 1 over root square of mu 0 epsilon 0 equals to 3 times 10 to the 8th meters per second, which is the speed of light in vacuum, right? As we know, approximately, right? So it's very close to that number. So the wave number is the angular frequency divided by the speed of light in vacuum. So that's the wave number in vacuum. Wave number plays a very important role in determining the properties of propagating waves, either in a material medium or in vacuum. Wave number in vacuum, right? So when we define the wave number, we obtain for E an equation which is on the form Laplacian of E plus k0 squared times E equals 0. And for H as well, we obtain the same equation, Laplacian of H plus k0 squared H equals to 0. And this is the form of Helmholtz. Equation, right? Is a second order partial derivatives differential equation. So if we break E or H in Cartesian components, right? So suppose that one component or E or H, so let's look into the solution of Helmholtz equation in the rectangular coordinate system. So if we break either E or H into components, let's call either components. One component of E or H is, let's call it psi, okay? Psi is not the, is not the scalar potential that we dealt in the previous lecture. It's just the scalar parameter. So when you have a rectangular components, each component satisfies the equation, the Helmholtz equation for the scalar function, Laplacian of psi plus k0 squared psi equals to 0. What we want to do is to determine eigenfunctions of this type of equation. So with these eigenfunctions, with those harmonic modes, we can use them to sum them up to form more complex waves. So they are the basic Fourier components of more complex waves, right? Like the Fourier series is, I didn't notice. That might make a difference in the sound, so let me put it back again. It completely fell here. No, not there. Here. So, we always try to find these special solutions, which are the normal modes of the differential equations. Because with those normal modes, we can build more complex, solutions. Example, a sine function, right? A cosine function, a complex exponential function. These are basis functions for expansions of more complex mathematical functions. Complex function, exponential function, or sine or cosine function are the solution of an ordinary differential equation. Very simple one. And with that function, we can build very powerful analysis by just looking into the response of specific harmonics. That's what we do also in dealing with the Helmholtz equation. We seek for functions which are the product of independent functions, like so, f times g times h. Okay? We have to put the second one here. Put the second tape so this thing doesn't fall. I hope. Okay? So we're going to seek those solutions. Let's recall that Laplacian is the sum of second derivative operators. And when we apply Laplacian on psi, we only have a derivative of one of those functions, right? So what's going to be? This is going to be GH, omitting the arguments, d2f dx2 plus fh, second derivative, plus fg, second derivative, z squared, right? So that's what we have. Plus, Laplacian plus k0 squared psi, this is going to give us plus fgh, k0 squared equals 0. Then we divide everything by fgh. We're going to have a simple equation like 1 of f, 1 over f, then we have that, we arrive at that, important form of the differential equation in which we only have single variable dependence for each term, right? This is varies only with x, this varies only with y, and this varies only with z, and the combination of the things has to be constant. So the only possibility is that each term is a constant. Otherwise, I cannot satisfy this, I cannot balance this equation. So what do we do? I mean, the derivative is going to be a constant. We are going to conveniently call it. I'm going to put a sign. I'm going to define this combination as a negative number. Let's assume kx real, but we are going to see I can assume any parameter here. It can be even a complex number. There's going to be a meaning when this is complex. There's going to be a meaning when this is real. Okay, let's start with the choosing real constants. Put the new one here because this didn't work. It works now. So we are going to choose those separation constants like this. Another constant here. Always choosing negative because, well, I'm going to show you why. So by this choice, we have this balance. Kx squared minus ky squared minus kz squared plus k0 squared equals to 0, right? So it means that the constants have to be chosen so that k0 squared is the sum of the squares. Notice that this is determined by the frequency. K0 equals to omega over c. C is the velocity of light in vacuum. K0, omega is the frequency that you impose into the field, right? So this is the number well defined. So this constant has to be bound by this relationship, right? Notice that the solution of these equations, let's say, we have a question like this. Similar equation for G and H. Solution for F is either sine function or cosine function, or we are going to employ in a more practical way complex exponentials. So I can use those types of solutions, right? Similar solutions for G and H. Okay. One specific combination, I'm going to use the minus sign, then we're going to understand what the sign means. Okay, so I have two linear independent solutions, right? Plus or minus jkxx, for instance. So one specific combination is this one. F times g times h, so exponential of minus j kxx, g equals to minus j kyy, and h minus j kz z, right? So that's a type of solution that we have, right? So in other words, minus j kx times x plus ky times y plus kz times z. Now we are going to start using our vector algebra. Recall that x is the position vector, right? So we have the components of a vector here, kx, ky, kz. We call this vector the wave vector. By definition, has components kx, ax, ky, and kz. So here we have psi equals, can be written as minus j wave vector k dot x. That's what one component would look like. So E or H, let's say E, is going to be a vector combination with an amplitude constant times this function in the x direction plus another constant times this function in the y direction, and so on. So the field solution is something like this. A constant vector exponential of minus jk dot x. Okay? That's the solution for the field, E field. So in our analysis at the moment, k is a real vector. These are real components, okay? So this is a phase factor. K dot x is a phase. It's so many radians. K dot x, right? Length to the minus 1 times length is a number, which is going to be a phase because it's the argument of a trigonometric function. Okay? So once you determine the E field, which is a complex vector, right? Even if your E0 is real, this is a complex number in general. So what's the physical field? Well, is the real part of E0 exponential of minus jkx times exponential of j omega t. Assume that E0 is real for an instance, okay? E0 is real, so I have a real part of this function here. So E equals to E0 cosine omega t minus k dot x. For a given time, fixed time, this is a function of the coordinates, a periodic function with the wave vector having, you know, a scale factor. Let's look into that. Let's assume that k equals to a magnitude, the versor, the unit versor u. If I choose x parallel to u, so k dot x equals k0 times x. X is the, you know, the quantity. So E equals to 0 cosine of omega t minus k0x. If you wanna set the phase constant, if you're gonna keep the phase constant of the cosine, what do I have to do? What would be the velocity of an imaginary, a fictitious observer to always see the same wavefront, the same phase? So I have to keep omega t minus k0x constant. So if you make a derivative relative to time, I have omega minus k0 dx dt equals 0. So I have to make, the observer has to be at the velocity equals to omega divided by k0. Well, but k0 is omega divided by c, so it equals to velocity of light. The phase velocity is equal to the velocity of light. So if I look into this wave, right, if I take a picture, instantaneous picture of the wave, of the amplitude of this wave, it's going to look like this. Oops. Things are moving here. It's going to look like this, right? Take a shot, picture. So the amplitude of the E field changes periodically in space for a given time and change periodically in time for a given point in space. Let's look at the space. So the period, which we call the wavelength, because we are in vacuum, this is going to be called the vacuum wavelength, equals to 2 pi divided by k0, which is the wave number, right? So it's going to be 2 pi here, divided by k0, which is omega over c. Omega is 2 pi times the frequency f. So we have that very well-known relation, wavelength relative to frequency, right? So high frequencies, low wavelengths, small wavelengths. Low frequencies, long wavelengths. You know, high frequency, the space variation is very fast, high frequencies. And the low frequency space variation is very slow, large wavelengths, right? So we have names for those quantities. We have to recall. We have to make the difference between frequency and angular frequency. We have also to recall that. I mean, when we talk about omega, we are talking about the temporal angular frequency, radians per second. K0 is the dual parameter in space, right? This in fact is the spatial angular frequency, radians per meter, right? T is the temporal period, it's a period in time, and lambda is the spatial period, which is the wavelength, okay? Omega is 2 pi times f, traditional temporal frequency. K, which is the wave number, is 2 pi times the spatial frequency, cycles per meter, right? So we have frequency inverse of period, time period. Spatial frequency is equals to inverse of the spatial period, which is wavelength. So these are dual relations, okay? So let's now derive the canonical form. Canonical. Well, the canonical form, this, I think this is misspelled here. Canonical form, canonic form, canonical form, I believe that would be canonical form, yeah. That's right. It's not canonic, but canonical. So that's not right. Canonical. So let's derive a canonical form of the plane wave. So a canonical form has a specific way to represent E and a specific way to represent H, and vice versa. And 2 ways, in fact. Okay. Given the E amplitude, we have a way to represent H. Given the H amplitude, we have a way to represent E. So let's look at how would be that representation if I have a E represented by this. So we're going to have some important properties. Okay. If I calculate the divergence of E, is the divergent, okay, divergent of a vector times a function, right? Function times a vector. Chain rule, F divergent of the vector plus vector dot gradient of the function. Now we want to calculate divergent of E. Let's look what it is. Divergent of E0 exponential minus j k dot x. This is equals to chain rule, right? The function is a complex exponential, and the vector is a constant vector. We don't have this term here because vector is constant. This is going to be E0 dot gradient exponential minus j kx, right? So, well, this is easy to calculate. This is minus jk exponential. Well, I think I asked you to do that in the first homework, so I hope you remember that, right? So it equals minus j k dot E0 exponential, and this equals to 0. So it means that this dot product is 0. We are talking about the real vectors. K is a real vector. Okay? So we have to be careful in interpreting what those things are, right? For a real vector, this means that K and E0 are orthogonal vectors, okay? For a complex vector, that's not really true, because for a complex vector, K and E would not have a meaning, a geometrical meaning. They are in complex numbers. We have to bring them back to the time domain to see what is the connection between directions. But if K is a real vector, this would mean that K is orthogonal to the field E in the time domain. Okay, try to look into that question and see what you conclude. Okay, I'm going to leave that to you. So let's interpret that K and E0 are orthogonal vectors. K is a real vector, right? So that would be, if E0 is a real vector, this means that these vectors are orthogonal. K and E0 real. Okay? So that's what it means. If E0 is a complex vector, this would mean that K is orthogonal, K is a real vector, is orthogonal to the physical fields. Okay? So, so that's what we have to look at. So that's the first property. Well, the property is this one. K dot E0 equals 0. Well, the other relationship we are going to use is that curl of E equals minus j omega mu 0 h. Then we can determine h. Okay, so I'm going to use the known result. I'm sorry. So minus, if I multiply by minus j, yeah, that's minus here. Sorry about that. So that's going to be minus j divided by omega mu 0 curl of, again, a constant vector times complex exponential, right? So this equals to minus j divided by omega mu 0. There's a chain rule again, right? This is minus E0 cross gradient of exponential, which is minus jk exponential. So minus and minus is plus, and j with j is minus, with minus equals 1. So it's going to be k divided by omega mu 0. Is this right? Is this right? Let me do it. Minus E0 cross the gradient, which is minus jk, plus so it's going to be E0 cross k, right? I think I made a mistake here. Minus j. Let's do it carefully. Minus j divided by omega mu 0. Then we have plus j, oh, sorry, yeah, is 0 cross k exponential minus jk dot x. Oh, now it's correct. J with the minus j equals to plus 1, right? I think there's a wrong sign here. Let's review the calculation again. H equals to curl of E. Let's do it carefully here. Let's do it carefully. It's minus 1 divided by j omega mu 0. Oh, that's the mistake. So it's going to be plus. So there's a mistake in the class notes. There's a mistake in the class notes. That's what's wrong, right? Yeah. There's a mistake in the class notes. So that's plus here. Plus. Then it's going to be minus. Is 0 cross k. And I'm going to change the sign. Then it's going to be plus. K cross is 0. Well, that's E, right? So it's K divided by omega mu 0 cross E. That's what H is. Okay? So let's elaborate a little further. H equals to K cross E. Right? That's the result. E is given by the exponential function, and K is given by this. Let's call K a real wave number, K0, times the unit number, versor U. So this is equals to, K divided by omega mu 0 equals to K0 over omega times U, which equals to omega time divided by C, right? So this is going to be omega divided by omega here. It's going to be 1 divided by root square of mu 0 epsilon 0 times U. This has a dimension of impedance, right? We call this the wave impedance of vacuum. Let's see the number we get. 4 pi times 10 to the minus 7, 10 to the minus 9 divided by 36 pi, approximately. So it's going to be 36 times 4, right? It's going to be 2 times 6. Then we have 10 to the minus 9 becomes 10 to the 9, 10 to the minus 7 is 10 to the second times 10. Then we have a pi square, it's going to be a pi. So that's 120 pi ohms. So Z0, this parameter, the vacuum wave impedance is 120 pi approximately. That gives 367 ohms approximately. So with that definition, the canonical form becomes 1 over Z0 U cross E. That's the H field. So if you want to do that, that's going to be E0 exponential minus jkx. You see that field is volts per meter. This is no a-dimensional. Divided by the impedance, it's going to be amps per meter. It's going to be the H field. Okay. Something I didn't mention, right? what is the meaning of the factor minus jk dot x? Right. Well, that means a wave that propagates along the direction of k equals to k0 dot u. Okay. That's what it is. If I had written exponential of plus jk dot x, that would be a wave propagating along the direction of minus k. So here is like exponential of minus j minus k dot x. So it's a wave that propagates along the other direction, right? Minus k. So let's see. Let's go back to the canonical form. E equals to E0. We only have to use this form because whatever sign we have here depends only on the definition of the wave vector. To what direction does it point to? So when we have that, we have H equals to 1 over Z0 U cross E. Canonical form, right? Okay. Well, I can also, notice that E is orthogonal to K. Let's forget about the complex vector for a minute. Let's assume these are all geometric vectors. E is orthogonal to K, right? Because we showed that K dot E equals 0. We can also, if we go to divergence of H is of the form H0 exponential, right? So for the same reason, H is orthogonal to K, right? Well, we can see here, H is orthogonal to U, which gives the direction of K. And H is also orthogonal to E, and is given by this relationship. So I have a E, right? I have U or K. E cross H, U cross AE gives the H direction. It's going to be something like this. And E cross H gives the direction of U, right? Because H gives the direction of U. So that's the relative, the way that these waves behave. I mean, this is a cosine function, let's say, real function. Let's say that we have all complex vectors are real, then we have only the cosine function that is important. K is the direction. A constant phase is a plane, okay, because along this plane, the amplitude of the wave is constant. So if the field orientations are those shown in the picture, E, H, and the direction of K is that, it's the same direction of E cross H. Okay? And the canonical form is like this. Right? That's a way of writing the canonical form in terms of E. I could write it in terms of H. So let's just show you how it is. I can, can write H equals to H0 then what's going to be E, huh? Well, let's recall H0 equals to U cross E0 divided by Z0, right? That's what H0 is. If I make a U cross H0 times Z0, it's going to be U cross E0. Then I have a triple product, so it's going to be UE0 times U minus U dot U times E0. Well, that's 1. And this is 0. So this minus is 0. So E0 is going to be minus Z0 U cross H0, right? So that's the canonical form. U equals to minus Z0 U cross H. That's the canonical form expressed in terms of the amplitude H0, right? Just only changes that we have a minus sign. So it's the voltage equals impedance times current. It's the same thing. That's how we look at those forms. So let's conclude our lecture with the canonical form, right? We are going to look into the power density and the energy when you have, a vacuum propagation, have a harmonic plane wave in vacuum. Let's look into Poynting vector. Well, recall that Poynting vector is half of EH conjugates, right? So if we use the canonical form, let's look what that is. The Poynting vector, right? Poynting vector, using the canonical form, we can use, let's say, Poynting vector equals to half of E cross H conjugate. And by use of the canonical form in terms of H, in terms of E, so we have H equals to 1 over Z0 U cross E. So the conjugate is going to be the conjugate of U. U is a real versor. So they're going to be, U is a real versor, just the conjugate of E. So this is going to be 1/2 of E cross Z0, right? U cross E conjugate. So this is going to give us the triple product is this dot product with the third vector times U minus E dot U, which is 0, times E conjugate, right? So that's the Poynting vector. 1 over 2 Z0, magnitude of E, direction of U. Very simple relationship, right? Voltage squared divided by impedance, but that's density, so it's area, per unit area. Notice that E squared equals to E0 is the amplitude is 0 square, because exponential, the magnitude of exponential equals 1. So that can also be written like this. The amplitude is fixed times U. Very simple relationship, right? I mean, very nice, simple results are predicted. Well, energy density, electrical energy density, is 1/4 of ED conjugate, right? Well, the conjugate is epsilon 0 E, so that's epsilon 0 over 4 E square, right? Or E0 square if you wish, right? If you want the WM, the energy density is 1/4 of BH conjugate, which is mu0 H square, mu0 over 4 H square. These are a real number, right? Because it's like that. In vacuum, energy densities are real numbers. Well, if we make the ratio WE divided by WM, it's going to be epsilon 0 divided by mu0, ratio between E and H squared. Well, that's Z0, right? Squared equals to 1. So the energy densities are equal. So the system is balanced. The net energy, electrical minus magnetic, electric minus magnetic equals 0. So that's a very nice result. The electromagnetic energy is the total sum between the two. Which equals either 2WE equals 2WM, right? So you see that when you calculate the Poynting vector, let's just make a parenthesis here. If I calculate the flux of S inwards a volume, the first term is J conjugate dot E, J equals 0. The second is J2 omega over 4 electrical energy minus magnetic energy. Because the densities are the same, this is equals to 0. So it means that the power flux inwards, the net power flux equals to 0. Vacuum doesn't absorb energy. That's the meaning of this equation. What enters goes inside, just flows outside. Nothing is absorbed. No net result. Okay? So that's what we would have in vacuum. Let's look into that. I mean, the electromagnetic energy equals to 2WE or 2WM. You see that, let's say, the electromagnetic energy equals to epsilon 0 over 4 times 2, right? So epsilon 0 over 2 E squared. So you see that this is equals to, under Poynting vector, the magnitude of Poynting vector is equals to 1 over Z0 E squared. So that's, root square epsilon 0 divided by mu 0 times E squared. I can make the ratio between these two quantities, the electromagnetic energy total divided by S equals to you see, it's going to be epsilon 0 divided by root square epsilon 0, and times root square of mu 0 is going to be mu 0 epsilon 0, which equals to 1 over c, right? So the Poynting vector equals to the velocity of light times the electromagnetic energy. It's like the power flow equals to the, energy that moves in space with velocity c. Time rate of change of energy is the power density. Velocity times electromagnetic energy density. Let's see if that makes sense, okay? Consider this volume in space. Power flows across this area delta sigma. That's the power density S, the Poynting vector. Let's assume that at a given time instant, some energy enters one face of the volume. After some time delta t, right, the energy comes out. During this time, because of the velocity, the energy propagates at length delta L. So the power that flows, okay, comes in and arrives at the other side at a velocity delta L delta t. What velocity is that? Well, let's calculate the energy inside of the volume is the energy density times area times delta L. So if we make the rate of change of that energy, how much energy is entering per unit of time, just divided by delta t, which is the time spent by the wave to go over a length delta L. So it's going to be delta L delta t is going to be the velocity of flux of energy, right? So this is going to give us velocity times delta sigma times energy density. So that means that is the flux, right? S delta sigma. So it means that the flux, the power density, equals the energy density times the velocity. So the velocity of energy flow is equal to the velocity of light, as we just demonstrated. Okay? So that's the meaning. That's why we have that relationship. All right? Okay, so we conclude our lecture in this topic. Okay, in the next lecture, we are going to see how materials respond to the application of a field. We are going to derive a general property of materials. How do they behave when you apply, a harmonic field? How do they respond? Okay, and that's going to be the starting point to understanding the concepts of losses and dispersion in a medium. So we conclude the lecture here. I hope to see you next time. Until then, bye-bye.